Okay, good morning, everybody. This is Mr. Steele. Not literally, because I'm not here. Like, that would create, like, I don't know, like a wormhole or something. But anyway, since I'm not here today, I'm at a workshop for Avid up in Mather. I want to make sure you guys still had your lesson. You guys are still able to keep going. So, we're ready to go here. So, basically, what we're going to do is I'm going to go through the lesson just like I normally would. The only difference is you can't ask questions because even if you try, I won't answer them because I can't anticipate what all of them are. Well, except for one thing. What's that, Bailey? Oh, you say it's not the 55th of November? Oh, my bad. I think you need to look harder. See? It says the 5th. See? I don't know what you're talking about, Bailey. Shameen knows what I'm talking about. Okay, so anyway, what we're going to do is we're going to go through and finish the second half of kind of what we did yesterday. Yesterday, we worked through and figured out how to factor. Today, we're going to work out how to solve when we're given that little bunch or the little bump and a little bit of a push that comes from the factor remainder theorem. So if you need to, please pause the video for a second so that everyone can copy down the essential question, title, date, notes, all that stuff, and then come right back. Okay, assuming that you already paused it. If not, this is just kind of awkward, so oh well. Basically what I want to start with is a problem that kind of motivates why we're doing what we're doing right here. And that is if I ask you to graph a polynomial that's written in what's called standard form. So basically, not that we'd ask you for it right now, it's something we'll look at in the future. But basically, this polynomial is in standard form because it's basically written out as a series of terms, all being added or in this case subtracted sometimes together. So if I wanted you to graph it, you might be able to plug in points and make a table of values, but it wouldn't be able to get you that same cool little noodle bowl the same way and as quickly as we did it in the past. So what we might want is to be able to factor this guy, because if we can see this guy in what's called factored form as a whole series of parentheses, well, then we can go ahead and plot the zeros and we can fill out everything else from there. Like, basically, it's not hard to see everything from that point on. So what we're going to do here is we're going to start by basically using what we did yesterday to graph this polynomial. We'll do it really briefly. It's not going to be something long. It's not going to be like Graph-A-Dash where we're going to spend a lot of time on it. Just going to go through it really quickly and do it. So first of all, if I asked you to factor this guy, you would fail because basically we don't have a tool that will handle a polynomial that has 4 terms but doesn't factor out in the nice way. Like, you can kind of see right now that right on these first 2 terms, the GCF, if we pulled it out, would be x squared. On this side, the GCF would be, well, negative 1. So unfortunately, that's not going to help us. We're not going to be able to get where we want to. So for this guy, I'd have to give you one more piece of information. So I would say graph that polynomial given, let's say, x plus 5 is a factor. So just like yesterday, that way it kind of starts the problem off the same way as before. So if this were a problem from yesterday, and I'd given you this as your setup, like you're given that x plus 5 is a factor, you'd go ahead and write out 2 SPACs and then work your way through from there. Well, I'm not going to do that just for this moment because, of course, that's not our goal. Our goal is to graph this thing, so let's not, bog ourselves down. Instead, I'm going to use the fact that x plus 5 is a factor in order to do synthetic division to break this polynomial up so that I can get a quotient that I can factor and I can actually work through. Excuse me. So from here, if x plus 5 is a factor, I would do synthetic division with a negative 5 up there, put in the coefficients, just like I have in the past all the time. So that's a really crappy 7. I'm sure someone out there is going to say something about it. So that's also a crappy 7. That's also crappy. Less crappy. There we go. So we can do our synthetic division. So bring down the 1, negative 5, negative 9, 45, 8, negative 40, dun 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 dun. We got remainder 0, which is good because it's not a factor if it's not remainder 0. We're kind of stuck there. As far as our quotient, we end up with x squared minus 9x plus 8. And then this guy is what we need to factor in order to see all of the individual factors for this polynomial so that we can graph it. So I can do a quick diamond. This one's an easy diamond problem. So plus 8 minus 9, we'll get minus 8 and minus 1. If I factor it with the easy diamond, I get x minus 8, x minus 1. And so if I were to write out a completely factored version of this guy, so I don't know, draw a perfectly straight line. Gosh, you can't get any better than that. Perfectly straight line. And I want to write out my factorization, which would allow me to graph it, of course. So if I write out my full factorization, I'm going to have the x minus 8, x minus 1 that I just found. And then, of course, I'm going to have my given piece. Like that one that allowed us to start this problem that we couldn't before. So from here, x minus 8, x minus 1, x plus 5. Why does that help us? Well, because now, this guy, we can graph. It's like, I can do that. I can graph that. Like, basically, I see 3 different zeros, 3 factors, no bounces, no slides. I can look at this and I can recognize that it's a noodle because it's a degree 3. I can see that I've got 3 zeros at positive 8, 0, positive 1, 0, and negative 5, 0. And since A is positive 1, that means I've got a positive noodle that will go like this. So left end behavior will be negative infinity, right end behavior will be positive infinity. So basically it might not be perfect, but I'm going to get something that looks a little bit like, I had it for a second. Oh, polynomials are so fleeting. We'll get something along those lines. So basically there's our graph. So in the past, when we started, we really couldn't do anything here. We were just kind of stuck because it wasn't written in a nice form for graphing. But by using some information that we were given, in this case by knowing that x plus 5 is a factor, we were able to break down the polynomial until we got to this point, where it turns out this y value, y equals, is the exact same thing as this. This version, the factored version down here, is just something we actually know how to graph from. And we're able to really quickly turn out that graph. So lovely, that's great. Just shows us that if we have a little bit of information, if we're given a little something to work with, we can basically turn any polynomial into one that we can actually play with, factor, solve, whatever we want to do with it. So good job. Keep that in the back of your head. Questions? Right, yeah, I can't answer any. So good deal. Okay, well, so with that said, what is it we're going to do today? Like, we're really not adding that much in here. We're doing something really small. But at the same time, I want to kind of refresh you on a couple pieces that we need to look at. So the first thing that we're going to be using today is the one we saw yesterday. That's called the factor remainder theorem, and it's what we just basically identified and used in this last process. So if you recall, factor remainder theorem. Don't necessarily need to write this down again. I'm just writing it down for clarity's sake since I'm not actually here. It's easier for me to keep track of stuff when I'm doing it this way. So basically what the factor remainder theorem says is that there are 3 equivalent statements that all mean the same thing and that we can use to help us break down a polynomial that we couldn't do otherwise. The first one is if we know that x plus k is a factor, then we also know, and basically the symbol that I'm drawing right here means if and only if. It means in both directions this is true. It doesn't have to go just one way. If x plus k is a factor, then we know that, sorry, I wrote this wrong. If x minus k is a factor, otherwise it would just have been awkward. So if x minus k is a factor, that means that x equals k is a 0. We say 0, we really mean solution, but same different thing, same thing. And then of course if that's true, that also means that if we plug k into our polynomial, it's going to spit out 0 because of the fact that when you divide by something, you end up with the remainder that matches the value of the function. So we saw that a little bit yesterday. Not a big deal. Either way, for us yesterday, since we were trying to factor the polynomial, our key statement was the first one. Like we were always looking at, okay, x minus k, we need to include that down there. We need to use that to set up synthetic division. All those things. Today, though, we're going to take it a step further, and we're not going to worry about we're going to worry about factoring, but we're not going to stop when we get to the factoring. What we're going to do is we're going to take it one step further and actually ask, what are all the zeros for this polynomial? Like, why stop at just factors? Let's actually say, what are the zeros? And then when we do that, we actually want to look at one more theorem that we've also talked about in the past, and that is the fundamental theorem. The fundamental theorem of algebra. There is one of calculus, so I shouldn't just say the fundamental theorem. The fundamental theorem of algebra. And when we talk, oh, that was horrible. You can hear Bailey scoffing in the back. So, sorry, when we talk about the fundamental theorem of algebra, it's basically a way to connect the degree of a polynomial to the number of solutions, aka zeros, that we're going to end up with. So what did that fundamental theorem say? It said that the degree, in other words, that highest exponent, whatever that highest exponent is, the degree of a polynomial is the same number, or gives the number, or I'm just going to say is the number of zeros. And of course we said that the last time we could have some duplicates when this happens. You know, there's always a possibility where we have to count like 0 twice. Not a big deal, but just something in there. So basically the fundamental theorem is a way to tell us how many solutions we should expect. So if you're thinking about it, how many zeros or solutions should I get? It's a way to check your completeness. Like, it doesn't tell you how to find them. Like, we're stuck with the factor remainder theorem in order to find them, but it tells us how many we should get and allows us to tell if we actually have all of them. So today, what we're going to be doing is we're going to be combining these two theorems. Like I said, basically what we're going to do is we're going to start with a problem that requires the factor remainder theorem, just like we did yesterday. You know, it'll say for f of x equals blah 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 blah, given that blah 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 blah, find all the zeros. So basically we're going to give you that little push just like before. We're going to give you that one piece of information that you can then figure out how to factor the polynomial from, and then we'll just finish by solving and checking with the fundamental theorem of algebra, checking with this guy to tell whether we've gotten all the solutions. So it'll be kind of a tiered process. So if you don't have it already, if you could take that half sheet of paper with the problem set up on it, or if you could have Miss Bravos, if you could pass that out right now. You can pause the video for a second, pass out those half sheets. We're going to use that in the first couple examples here. So thank you. Okay, so let's look at our first full problem now that you got that half sheet. So as of right now, it doesn't say much because we have to fill in the actual problems themselves that we're going to play with. So if you could fill this in with me, basically the polynomial we're going to start with, for the first example, maybe on the left-hand side of the half sheet, is going to be 6x cubed minus 13x squared minus 41x minus 12. And we are going to be given, in this case, that x minus 4 is, it's taking up too much space. X minus 4 is a factor. Can't spell factor. Now I can. Okay, so there we go. So 6x cubed minus 13x squared minus 41x minus 12. If you were to look at that and think, hey, let me just factor that by grouping, yeah, it's going to fail. Like, not going to go well. Go ahead, try it. Yeah, failed. That's what I thought. So instead, what we're going to have to do is we're going to actually have to use the factor remainder theorem from yesterday and figure out how we can use this information, use the fact that x minus 4 is a factor, to break this puppy up. Actually, that's kind of gross. Why would you want to break up a puppy? That's terrible. To break this polynomial up. Better. So, for where do we start? We are going to start in the same place that we did yesterday. We are going to begin by stating the implied facts. So, and what I mean by that is we're just going to fill in those two lines of information right underneath the information of the problem itself, just in case we need to use one of those pieces of information. Yesterday, finding the one that said something about the factor was really powerful. It's still going to be powerful, but today, since we're trying to actually find all zeros, it might actually be more valuable to have a second one. So, how do we do that? State the implied facts. We go back to what it says in the factor remainder theorem. So we're looking right about here. And what it says is that if x minus k is a factor, then x equals k is a 0. So our first fact is if x minus 4 is a factor, then x equals 4 is a 0. It's that same connection we make when we graph, where we say, oh, if x minus 4 is in that polynomial, then we can just do the opposite or set it equal to 0 and solve, and we're able to get out the 0. The other part from the factor remainder theorem, still right about here, says that if x equals k is a 0, then f of k equals 0. Basically, if you plug in that number, you're going to get 0 out. Well, that's fine. Basically, in this case, f of 4 equals 0. And so from here, we stated the two facts. So now, right at this point, one of the nice things is that since we've stated these facts, we actually already know something in our answer. What is it? Come on, someone raise your... Oh, yeah, that's right. I'm staring at a computer screen, not you guys. That's awkward. So yeah, you can't actually answer that. But basically what I was going to say is if it tells us that x equals 4 is a 0, and we are trying to find all zeros, we can automatically, right off the bat, write down here that x equals 4 is a 0. Why? Because it says so right up here in the implied fact. That was implied based on the information that they gave us. So right away I've got 1, 0 down there. I can feel really good about myself. I've got one. Okay, so now we've stated our 2 implied facts. Nothing's changed from yesterday. Our next piece, though, is going to be a little bit different. The second thing we're going to do is just create like a little check. We're trying to kind of make ourselves aware of how many solutions we're trying to get. So the next thing is we use the fundamental theorem. I'm going to abbreviate that, the fund-thumb, to find out how many solutions, or in this case not solutions, how many zeros we need. So in fact, this is probably the easiest step of the entire process. It's new, we didn't do it yesterday, but it's the easiest part of the process. So right up here, I'm talking in this general area, so put it in a nice pink box for the second so that you can see it. In this area, we've got to figure out what's the degree and how many solutions does that mean, knowing of course that the fundamental theorem says the degree is the number of zeros. So when I look at this guy, I figure out what my degree is by looking at the exponent here. So the biggest exponent is right on there. It's a 3, so that means that we have degree 3, and that means by the fundamental theorem of algebra that we have 3 solutions. So right now, we've only got 1. We're missing 0, number 2, and 0, number 3. So we're short a little bit here as we go forward. So we need to find 2 more. You can't see it, but I'm actually making 2 fingers right now, right at the microphone. No, that's kind of dumb, but oh well. So great, good job. We got our first 0. We figured out how many we need. Our next piece is to go straight into the factor remainder theorem. So basically, what we're going to do is we're going to use synthetic division. And we're going to use that to break it up. Basically, our thought is if we divide by something we know is a factor, we're going to be able to break up this polynomial into a piece that maybe we can factor. Because right now, we're out of luck. Like, there's nothing we can do. But if we factor this guy, or if we use that x minus 4 as a factor thing and break it apart, we'll have something we can play with. So in this case, if x minus 4 is a factor, that means my pivot is going to be 4. I can write in my coefficients, 6x cubed minus 13x squared minus 41x minus 12. And then I can set up my synthetic division. Wow, look at that beautiful line. Almost perfect. I can set up my division and work from there. So again, doing the synthetic division isn't hard for you. 6 times 4 is 24. That leaves us with 11. 11 times 4 is 44. That would be 3. 3 times 4 is 12, which means my remainder is in fact 0, which is cause for celebration because it has to be 0. If it wasn't 0, we screwed up, or else I was lying to you in the first place. And would I lie to you? No, I wouldn't. Discount that. Okay, so we've done our synthetic division. Good for us. Like, pat ourselves on the back. The problem is, what do we have to do from here? Basically now is when we get to use all those factoring strategies we've accumulated up to this point. We're going to factor the quotient. So you can kind of see that this is feeling a lot like yesterday. Kind of that deja vu feeling. So we're going to factor the quotient. In this case, our quotient is 6x squared, because 6x cubed divided by x minus 4 gives us x squared. 6x squared plus 11x plus 3. I've got to factor this guy. It's got 3 terms, no GCF, so I'm thinking diamond. So 6 times positive 3 is positive 18. Positive 11 is what we've got to see what they add to. So now I need 2 numbers that multiply to 18 add up to 11. Do, 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 do. Okay, I'm done. I was going to call on someone like, hey, Marcos, what'd you get? Good deal. Good job, Marcos. Got positive 2 and positive 9. So those are our 2 pieces. So now since there's a 6 in front here, we can't use the cheap easy diamond. We have to actually split it up. So I'm going to use split the middle. It's my favorite go-to strategy. So we're going to split this guy into pieces. Again, we're just trying to break it up so we can see what those other 2 factors are. So let's see. GCF of the first part, I'm seeing a 2x. I'm thinking a 3x plus 1. Over here, I'm seeing a positive because it's closest sign. Plus 3, 3x plus 1. And that's going to leave me with, as my factors, 2x plus 3, 3x plus 1. So good deal. I factored the quotient. I factored whatever was left over after I did my synthetic division. So yay, good job for me, but I'm not done. Why am I not done? Well, because I'm not being asked anymore to figure out what the factors are. It doesn't say factorization down here. It says zeros. So of course my last piece is to get all the zeros. So my last piece is to, I don't know, set it equal to 0 and solve and figure out what they are. So it's as simple as just saying, when are these two guys equal to 0? Well, the first one could be equal to 0, in which case if we make that so, we can subtract 3. We'll get negative 3 over 2. On the second one, we'd have 3x equals negative 1. We would have x equals negative 1/3. So as it turns out, we have a 0 at negative 3 over 2, and we have a 0 at negative 1/3. So the last thing though, like we are done, we did solve the problem. But just in case we weren't sure, our last piece is to check with the fundamental theorem. So basically all that means is nothing fancy, there's no real math work here except counting. Like you can do that on your fingers, can't see them, I'm waving mine. I go up here and I say how many solutions did I need? I wanted 3 solutions. When I go down here, I can count it. I've got 1, 2, 3. I have 3 solutions. That means I've got all of them. I did my job. I was able to find all the zeros of this polynomial, and I just needed that one little piece of information to do it. So that's our plan. That's going to be our strategy as we go through this entire thing today. So notice we got 3 solutions. Degree was 3. Everything worked out fine. Questions? I wonder if any hands went up. That would have been kind of embarrassing, but in an endearing sort of way. So there we go. First problem out of the way. Alrighty, so one problem down, another one to go. Basically, I'm just going to do 2 examples. This is my second one. What can I do to, throw a wrench into the process or throw you something a little bit different? All I can do is make it bigger. Bigger, badder, longer. So here we go. So let's see. So our f of x this time, let's go to the 4th power. Let's make it a little old quartic. 4x to the 4th minus 15x cubed plus 49x squared minus 150 x plus 90. And then let's use the fact that we're given that f of 3 equals 0. Now, you know what? Someone's going to complain about that. F of 3 equals 0. So there is all our information that we'd be given. Like, there's basically our problem. So take a second to copy it down. So as we approach this guy, crack those knuckles, crack the knuckles, get themselves ready. Okay, here we go. So ready to go. You know what? I'm just not feeling it. I think we need a little bit of background music here to get the energy level up in this room. Because even though I can't see it, you guys are like clockwork. You're probably sitting there staring, going... You can't see it right now, but I was just staring blankly forward like you guys tend to do. So let's throw a little music in there. How about a little bit of epic primetime music? Okay, so we're starting this problem off. What are we going to do first? We're going to state the implied facts. So we're just going back to the factor remainder theorem. So fact 1, we already know that f of 3 equals 0. So thinking back to this thing, if f of 3 equals 0, then x equals 3 is a 0. So x equals 3 is a 0. And then our third connection is the factor. The factor is the one that's always opposite from whatever we do from the other one. Just like if we're graphing, if x equals 3 is a 0, that means x minus 3 is a factor. So bam, there we go. Got it started out. Okay, so factor remainder theorem part's been used. Next, let's just do that little catch. Let's just make ourselves safe here. So what's my degree of the polynomial? Everybody. 4. Yes, good job. Your voices sound funny. But the answer is 4. The degree is 4. Why? Because we've got the power 4 right up here. And that means there's going to be 4 solutions. Although some might be counted multiple times. So let's go from here. First 2 steps down. It's time for a little bit of epic synthetic division action. So we've got x minus 3 as our factor. So we're going to use 3 as our pivot. We've got a lot of coefficients. Let's get started. Negative 15, positive 49, negative 150, 90. The 9 disappeared. There it is. So we want to do synthetic division. So let's roll with it. Let's get this guy up a little bit, just not a lot of space. Okay, so we're going to roll. Bring down the 4. 12, negative 3, negative 9, 40, 120, negative 30, negative 90, 0. Booyah. That's exactly what we had to have. If it wasn't 0, we screwed up. So good job. Pat yourselves on the back. And we've got the synthetic division part. So we've broken it up. Why did we do that? Because we wanted a quotient. We want to know what is the rest of this polynomial. If we know that one factor x minus 3, what does the rest look like? Because maybe I have the tools to factor that remaining part. Let's see. 4x, well, let's see, we started with 4x to the 4th. We divided by x minus 3. That's going to give us 4x cubed minus 3x squared plus 40x minus 30. So I've now got to break this guy apart so that I can solve all those factors from there. So looking at it, I see 4 terms. I'm naturally going to think of grouping, factor by grouping, where we've got 4 terms. So we could use splitting the middle or the box. Since I used splitting the middle last time, I'm going to use the box this time. So from here, how can you not be energized by this music? 4x cubed minus 3x squared plus 40x minus 30. Pulling out some GCFs here. Got a little x squared, positive 10, 4x minus 3. So this guy is going to factor into x squared plus 10, 4x minus 3. So there is my quotient all factored. Since x squared plus 10 isn't a difference of squares, I can just leave it as is. So I've factored my quotient, I'm through that piece. What's left? One more run. I've got to get all the zeros and check to make sure that I got 4. It says up here I've got to get 4, so I'm going to make sure that I get 4. So from right here, if I set each of these factors equal to 0, 4x minus 3 equals 0 is going to imply add 3 divided by 4. I'm going to get that x equals 3 over 4. On this side though, if x squared plus 10 equals 0, that means that x squared is going to equal negative 10, so that when we use the square root method, we're going to get that x equals plus or minus the square root of negative 10. Well, negative 10 square root doesn't exist, so of course that means we need an I times the square root of 10. So from this point, we can feel really good about ourselves. We got all the zeros. We've got negative I root 10. We've got I root 10. We've got 3 over 4. That gives us 1, 2, 3 solutions, 3 zeros. We're supposed to get 4. Oh crap. Oh shoot. Shoot. Whoa. Yikes. What am I forgetting here? I feel like something's going wrong. Like I've only got 3, it says I'm supposed to get 4. This is awkward. What is it that I need? Where am I looking? Oh yeah, you guys can't answer. That was weird. Okay. Yeah, so what am I looking for? I need to use this little fact right there. So it says right there, actually I wouldn't go on that side. It says right there that x equals 3 is a 0 based on the information that we had. Therefore, our last 0 is going to be x equals 3. And we could have written that right off the bat as soon as we wrote fact 1. We just didn't because, well, I'm trying to rush here so that I can watch Sleepy Hollow at 9 o'clock. So with that said, there is our second problem done. We're able to factor a 4th degree polynomial using grouping after we used the factor remainder theorem, and then we checked our answer with the fundamental theorem to make sure we had all the zeros. So pretty slick if you ask me. But you're not asking me because you guys won't be watching this till the future, so go figure. Alrighty, I think you're ready, and even if you're not, well, the video is going to keep going. So here we go. I'm going to give you one to try. Since I'm not here, I can't really answer your questions. I'm just going to give you one more opportunity to try it on your own, see if you can swim or see if you're going to sink, and then basically you'll be able to get the homework to work on that and the standard quiz corrections. So right about this point, if you could copy down the problem, just do it in the back side of that half sheet that you have. And then, Ms. Bravos, if you could please pause. Oh, that was supposed to work out better than that, but I was going to say like pause, like a little, whatever. So if you could please pause the video for just a second to give them a chance to work through this problem for a few minutes, and then come back and I'll finish it off for them. Okay, here we go. Hopefully you're back. You've already paused the video. So basically the things that were in here, the first thing is that fact 1, like basically I can get these guys really fast. Negative 8 is a 0, f of negative 8 equals 0, and that means that x, the opposite, is going to be a factor. So this is like the quick Cliff Notes version of it. So from here, my degree is going to be 4. So if I make a real quick switch, my degree is 4. I'm expecting to get 4 solutions, or in this case, I don't really mean solutions, I mean zeros. I'm expecting to get 4 zeros. So from looking at my first piece of information, since f of negative 8 equals 0 and negative 8 is a 0, basically that piece of information tells me that my first 0 is going to be x equals negative 8. So I'm going to write it down there right off the bat, otherwise I might forget it. And then I'm going to do synthetic division. Wrong color. Synthetic, the pressure is pressure mounting. So synthetic division time. So 1, 10, 14, negative 20, negative 32. So we'll draw the line. Oh, jeez. Negative 2, or draw a line. Negative 2, it's a line. I don't know what I'm talking about. 1, negative 8, 2, negative 16, negative 2, 16, negative 4, 32, 0. Good job, it works. We were able to break it up. Our quotient, what we're left with, is going to be x cubed plus 2x squared minus 2x minus 4. I'm going to break this up using grouping, so I'll use split the middle this time. I'll get x squared, x plus 2. Over here I'll get minus 2, x plus 2. Don't fall into that trap. If you pull out a negative, you have to change that sign also. So this guy's going to factor into x squared minus 2, x plus 2. So this is where my other 1, 2, 3 zeros are going to come from. From here, if I set each one equal to 0, that's going to give me either x squared minus 2 equals 0 or x plus 2 equals 0. This one on the right is really quick. I get x equals negative 2, so I'm going to throw that guy right down there already. It's kind of bigger than the other guy. I feel bad. For this guy, if x squared minus 2 equals 0, then x squared equals positive 2. So I'll square root both sides. We'll get x equals plus or minus the square root of 2. Square root of 2 is the square root of 2. So therefore, my last two answers are negative square root of 2 and positive square root of 2. And from there, I was supposed to get 4 solutions. It sure as heck looks like I got 1, 2, 3, 4 solutions down there as well. So in other words, it looks like I've solved this problem. Hopefully you got the same answer. If not, well, we'll have to deal with it tomorrow. So anyway, with that said, I've got 8 minutes before Sleepy Hollow, and I still have to edit the entire video together and put it all together and then put it on YouTube. So, with that said, this is Mr. Steele signing off. Hope you guys were able to get that. Hope you enjoy the rest of your day. And if you're seniors, I'll see you at Powder Puff practice. Thanks. Good night. Or good morning. Good morning. Bye.